Hi, this is Dr. Hayek and this video is about electrochemistry, and today we will be talking about the standard reduction potential. In my last video, I have introduced the galvanic cell and how can we build one. Please check the link in the description below to see this video. Once we build the galvanic cell, the remaining question is how can we calculate the cell potential? Before answering this question, we need to discuss the standard reduction potential of half equations. As you know, the redox reaction is the sum of two half equations, the oxidation and the reduction, and the cell potential is the potential energy of this reaction. If we can determine the standard reduction potential of each half equation, it will be easy later on to calculate the cell potential from the potential energy of the redox reaction. However, there is no way to calculate the standard reduction potential of half equations individually. Therefore, we will need a starting point and a reference. Consider the following galvanic cell, where zinc is at the anode and hydrogen is at the cathode. Zinc is getting oxidized and therefore is losing electrons, and the electrons are being transferred to the hydrogen at the cathode, and hydrogen is getting reduced. Every two hydrogen ions will take two electrons to form hydrogen gas, which will escape the solution. The voltmeter is indicating a cell potential of 0.76. If we assume that the standard reduction potential of hydrogen is equal to 0, therefore the standard reduction potential of zinc is going to be equal to the negative of 0.76, and the sum of both standard reduction potential will give us the cell potential. In a similar way, we can determine the standard reduction potential of other half equations, as you can see it in the following table. So now, do you know how to calculate the cell potential of this galvanic cell? Take the corresponding half equations from the table, then flip the aluminum half equation because it's an oxidation and it's happening at the anode. And when we flip the half equation, we flip the sign, or we reverse the sign of the standard reduction potential. Therefore, it's negative E0 is equal to 1.66. Now, to sum these two half equations, as you know from balancing a redox reaction, we need to multiply by two integers. We need to multiply by 2, the half equation of aluminum, and by 3, the half equation of lead. And a very important remark is that when you multiply the half equation by an integer, you do not touch the standard reduction potential. After that, when you find the redox reaction, you sum the two standard reduction potentials, and therefore you get the 1.53, which is the cell potential. Once a galvanic cell is built, we can describe it using what is called line notation. Now, the line notation, we started by writing the anode to the far left, the cathode to the far right, and then with two lines in the middle that will represent the salt bridge or the porous disk. Now, between the electrodes and the solution, we put two lines, and therefore, since aluminum is getting oxidized into aluminum 3+, so we put a line between aluminum and aluminum 3+, and lead is getting reduced to lead solid, and there is a line in between these two. Here's another example where a non-metal is used in a galvanic cell. We can describe this cell using the following line notation. The anode to the far left, the cathode to the far right, and then the two lines that will represent the salt bridge or the porous disk. Now, zinc is getting oxidized into zinc 2+. However, here we have used an inert metal as a cathode, and therefore now we separate the solution, which is the H+, and hydrogen gas by a comma, and we write it this way. So H+ is getting reduced into H2 gas. We can also indicate the concentration and the pressure in the line notation, as you can see it in the following example. I hope this video was helpful to you, so please like, share, and subscribe, and I'll see you next time.